Okay, so we're talking about, just to give you a little more picture of second order non-homogeneous equations, because what I'm doing is pretty much surveying the major things in the course, kind of picking the low-hanging fruit, things that are pretty easy to understand that you want to get in your head and make sure you've got for the rest of your life. Okay? They're just some simple premises that allow you to solve these equations, but of course there are some details, and the devil can be in the details. We want to get an overview. Now, you've already done this for homework. These are the equations of this form. Okay? And actually, I shouldn't have D over here. I should have, actually your book generally uses Q, so I'm going to use Q of T. Function of T over here. Not just a constant. Could be any function of T. Now, you could always do the thing I told you to do over here and solve the homogeneous equation, right? So we can say the associated homogeneous equation is AY double prime plus BY prime plus CY equals 0. Okay? And that's real easy to solve, as you did for homework. Let y equal capital A e to the RT. Now, capital A and little a are totally different symbols. Same letter of the alphabet, but they're totally different symbols. Symbols are case sensitive, so you never want to write a capital A when you mean a lowercase a. Okay? Always make sure you have the right case. So let y equal capital A e to the RT, etc. You already know what to do. Okay? Because that's what you did for homework. Okay? And then you get two solutions. And we'll say A1 and A2, you have different constants on them. Okay? And general solution you just add the two. Okay? Now, this is what you get usually. There's a case where R1 could equal R2, where your discriminant is 0, where your quadratic function gives you a repeated root, where the characteristic equation, the equation you get for R, factors into a perfect square, like R minus 5 squared, and you get 5 as a root twice. Okay? So I'm going to say usually, and if you get the unusual case, you got to do something else that I'm not going to tell you about, even though you go down to your hands and knees and beg me, I'm not going to tell you. Okay? Now, if I see tears, I might, but, you know. Okay? But you don't want to know right now. I'm giving you an overview. We'll go through the details later. Now, okay, well, that's great. Okay? Now, there's also the case where you get complex or imaginary solutions to the equation. That could happen. Okay? So we want to maybe see what happens there. So I'm going to tell you a little bit about that. This is basic premise, not hard to understand, but you got to keep reminding yourself, and you got to know at least where to quickly look on 2 pages of high points of critical ideas in case you forget, so you don't have to do a web search and beat your head against the textbook and hope something sinks in. Okay? So, we'll talk about that. We won't talk about the usually part yet. We'll get to that later in the course. Okay? Okay, now, this, of course, doesn't solve this equation. It solves the homogeneous equation. So that's your general solution to the homogeneous equation. If you add to that solution any solution at all to the non-homogeneous equation, in other words, if you can find a function y that, when you run through the derivatives and everything, gives you the q of t, then you just add that to this, and that encompasses all possible solutions. Okay? And there's another thing we'll talk about. You've got 2 constants here. If you just have one constant, then an initial condition, an initial point on that graph would be sufficient. Okay? But if you've got 2 constants, you need 2 points on the graph. Or a point on the graph and the slope at that point. And then you get a solution. Now we'll talk about that, but I just mentioned it right now. You know, we'll do that in more detail. Maybe sooner, maybe later. So you can adapt the process that you did for homework, where you take the point, project forward according to the slope, and so forth. If you've got an equation like this, then if you've got a point and a slope, well, you can put in the point, you can put in the slope, and then you can find the second derivative, which is the rate at which the slope changes, and do things, okay? So you can adapt that process, simple geometric process, but a little more complicated, and I don't want to stuff your brain full of stuff till you get your book, okay? But I'm just saying, the stuff we've done, you really have to have mastered. You really have to know these things. You really have to be able to do them. If you can't, if you have trouble with it, be sure you let me know, and we will go on from there. Okay? So, let's just look at an example of what I'm talking about, where you see if you can find a solution to an equation like this. I'm just going to make up an equation right here, just typical, like y double prime plus 5y prime plus 6y equals 0. Equals let's make sure that cosine of t. Okay? Now, the homogeneous equation is y double prime plus 5y prime plus 6y equals 0. And you understand from the homework that if you put in e to the RT, you're going to get r squared plus 5r plus 6. And that's going to factor into r plus 3 and r plus 2, giving you solutions negative 2 and 3. Okay? So I'm going to introduce something that I haven't done before. I'm just going to say your solution set for this equation consists of the set e to the negative 2t, e to the negative 3t. Now I'm skipping the steps in between because they're really easy. And I didn't see anything looking at the homework that showed me that you don't completely understand how to do this. So we got e to the negative 2t and e to the negative 3t. So our homogeneous solution is a linear combination C1 e to the negative 2t plus C2 e to the negative 3t. Okay? Okay, now, we want to find a solution to the actual equation, because this isn't a solution to this equation, because obviously if you plug these in, you're going to get 0, not cosine of t. Okay? So now we find a solution that yields cosine of t when you plug it in. Okay? Well, how are you going to get a cosine of t out of a combination of y and its derivatives? Well, if y was a multiple of cosine of t, well, then the y term and the y double prime term would give you multiples of cosine of t, right? So you get cosines very easily out of this, but if you use the cosine, you're going to have a sign here. I mean, you're going to get a sign here, right? Now, if you do multiples of sines, well, you get sines from this term and this term, but you get a cosine from this term. Maybe if you have the right combination of sines and cosines, the derivatives will work out. Okay? So try a trial solution. Let's try b sine of t plus c cosine of t. And that would be, I should have said y equals, but it's equal to y. So y is going to be this, right? So what I want you to do is plug that into this equation and see what you get.